Hello everyone, my name is Mustafa and I am PhD candidate from University of Campinas, Brazil. My area of research is quality of service and quality of experience in video traffic. In IEEE Globicom demo sessions, we provide two of our research work as a demos. In the first demo, we provide a framework for the evaluation of QoS and QoE using 4G and 5G use cases. And in the second demo, we provide a framework for the collection of YouTube quality of experience KPI with channel level matrices. In this presentation, YouTube goes 5G benchmarking YouTube in 4G versus 5G through open datasets. We talk about a framework for the collection of YouTube dataset with 1 second granularity such as stalls, buffer, video bytes downloaded along with other features. We also provide channel level matrices such as CQI, SNR, RSRP, RSRQ along with 100 other features, and we made this dataset public for the evaluation of 4G versus 5G in the wild with different use cases, and we can also infer quality of experience of YouTube KPI with this channel level matrices. Fifth generation 5G cell network users are increasing exponentially, where 5G coverage is a challenge for global telecommunication to provide end user maximum quality of experience. Compared to 4G, 5G is developed to address high bandwidth, low latency, and uh, massive connectivity requirements of enhanced mobile broadband compared to fourth generation LTE. So we provide a dataset for non-standalone environment. So what's the difference between non-standalone versus standalone? In non-standalone, 5G control plane lies on pre-existing 4G core networks, while standalone on a dedicated for 5G core networks. What is the motivation behind this work? As 5G technology evolves, its performance is expected to improve over time. Therefore, quality of experience of YouTube video streaming from mobile network operator perspective is ideal and challenging compared to 4G LTE networks. So, evaluating mobile carriers end-to-end network performance in the wild is unknown and difficult and complicated. Critical issues for mobile network operators include how to manage increased video traffic demand and provide satisfactory quality experience to their end user. To ensure better quality experience, understanding and monitoring the key performance KPI indicator KPIs that impact user perceived quality experience has become a trending topic. Therefore, we carry out a massive 4G and 5G dataset collection campaign using commercial 4G networks where we consider YouTube as a baseline for video streaming to collect channel level matrices and YouTube QE logs with 1 second granularity. So what was the problem? 4G and 5G have very different characteristics, making it difficult to compare them experimentally in a fair, efficient, and representative way. An investigation of YouTube quality of experience KPIs such as stall, quality shifts using commercial 4G and 5G cellular network in France under different mobility and static scenarios. A detailed performance of 5G non-standalone over 4G of YouTube QoE with 1 second granularity with YouTube player events and channel level matrices such as CQI, RSRP, and SNR. And what is a closer look at channel level matrices under different use cases to infer YouTube player interruption such as stall and quality shifts. So what is the solution? We use YouTube iframe data API to extract player information, stars, and quality shifts along with other quality experience KPIs. And we use Android application to collect channel level matrices, this CQI, RSRQ, RSRP, SNR, application download bitrate, among other 100 plus features. We open source our datasets to allow further analysis of network coverage and end user performance aspects, and we carry out an extensive benchmark of 4G versus 5G using YouTube as a baseline for objective QE stalls, shifts, among other features. So, what are the features that provided by YouTube iframe API? We have stall, we have resolutions, we have video bytes downloaded that can further provide per session objective QoE such as total stalling events, stalling ratio, stalling time, quality shifts, or percentage of time in a single resolution, dominant resolutions. And what are the features we providing as a for channel level matrices with the 1 second with 1 second granularity? Few features such as we have a timestamp, longitude, latitude, velocity, operator name, cell ID, network mode, what is the download bit rate, upload bit rate, what is receive signal receive quality, this RSRQ, what is receive signal receive power, RSRP, SR signal to noise ratio, RSSI, CQI, RSR, RQ, and RSP value of the neighboring cells among hundreds of channel matrices. So we use this application for the collection of these channel level matrices, which is available at this link. So we use different use cases such as pedestrian. We consider low mobility use case. Then we have driving, high mobility case. Then we have static, bus and railway terminals. And then we have static outdoor where it is high crowded. And we collected this data set in France over a period of 6 months. So this is the block diagram of the of data collection campaign. So we have YouTube API, YouTube iframe API that is running in the mobile browser. We run this web application in Chrome, and in the background there is this application is running that is collecting channel level matrices. So for the YouTube logs, we are saving stall, video bytes, downloaded resolutions, and which can further be used to find per session logs such as stall events, stall durations, quality shifts, dominant resolution, percentage of time in a resolution. And for channel level matrices, we have CQI, RSRQ, RSI, SNR, download bitrate, upload bitrate, state, events, among other 100 plus matrices. So what is the dataset statistics include? We have 300 plus kilometers of mobility use case. Then we have pedestrian, which is 100 plus kilometers. Then number of videos, we played 10 videos with different frame per seconds, 30 frame per seconds and 60 frame per second. Then total video sessions, we played 300 plus video session and 1500 plus minute of streaming. Then we have 4G and 5G data consumed 300 plus GB of data we use here. Then we have smartphone, which for the 5G we use Samsung Galaxy S21 5G, and for the 4G we use Samsung Galaxy S8. Okay, so for the results, we compare 4G versus 5G performance for these channel level matrices, and in the next few slides I'll also talk about the quality experience KPI for 4G versus 5G. So we're talking about CQI, which is channel level matrices for these use cases: mobility, pedestrian, bus terminal, and static outdoor. Same for 5G. We can see that bus terminal the CQI value is better as compared to other use cases, and similarly for 5G at bus terminal this value is better as compared to other ones. For the 4G, if we talk about RSRP, we see that bus terminal we have better this value, and also for RSRQ we have bus terminal, and mobility we have better RSRQ. But it is providing an opposite. We observe an opposite effect of RSRQ in case of 5G, where we see static outdoor and pedestrian outclass mobility and bus terminals. But in case of RSRP, it's showing a similar behavior as of 4G, and CQI value, as said before, that it is same as it is in bus terminal, but it is slightly higher as compared to 4G. Then we have SNR, signal to noise ratio for the 4G, and for 5G we see that even at bus terminals and railway terminals we have this better value for SNR. But in case of 5G, there is we have a better bus terminal, but at pedestrian we also see a slightly better SNR value at this point. Now I'll talk about the interruptions of 4G versus 5G, and we show the case mobility and the stalling events. We show case mobility for stalling events here, and we also show the handover events for 4G versus 5G. We can see that in 4G it's remaining in higher resolution. There is a stalling events, but we also experience stalling events when it is in lower resolution. Here we have HD 1080, and we experience the stalling events in 4G. But in case of 5G, we experience stalling events, but all the stalling events we experience are in high resolution. So we see that 5G is showing a little bit giddy greedy behavior here, because most of time it's remaining HD to 160. It's not moving, it's not going back to a lower resolutions to avoid stalls, so it's always remaining in high resolution even there is stalling events. So if we talk about the handover events in 4G, we see handover events for the 4G. At most of time, it's happened when CQI, which is the performance indicators, which remain. If it is near 6, then we have a handover events, and this is a session of a whole streaming session of a mobility pattern. So, but in case of 5G, we see lot of other handover events, which is intra and inter handover it, which is when we move from 4G to 4G, from one base station to another base station, there is a handover. When from 4G to 5G, another handover. And when there is a from 4G to 4G, and when there is another between 5G to 5G, so there are a lot of handover events. But we can see that all of handover events happened at when CQI value between 6. Now we talk about 4G versus 5G resolution. For the case of mobility, we experience very less quality shifts and raw resolution change between 4G versus 5G when there is case of statics indoor and static outdoor. So in case of 4G versus 5G quality shifts case of mobility, we see that in 4G the 63% of time it's remaining HD to 160, but in case of 5G it's remaining 99%, it's remaining in high resolutions, and 0.2% just in remaining 1440 resolutions. So we, as showed previously, even there is stalling events, it's remaining in high resolutions here in 5G, but we see that most of time it's remaining high resolution, but in case of 4G it jumps to a lower resolution. We see that HD 1440 25% is remaining here, and then there is also 3.2% it's remaining 1080, and there is also a change between its 480 resolution, which is 7%. So if we talk about pedestrian, we experience 95% 5G remaining in high resolutions, and very less percentage is remaining in other resolutions. But in case of 4G, it's just 37% remaining in HD to 160, and most of other is remaining in other qualities such as in HD 140 it's remaining 24% here, and 33% is remaining HD10. So uh, we experience that in 4G when there is some sort of low resources available, it jumps to a lower resolution. But in case of 5G, it continues to remain in high resolution even there is stalling events, as we discussed before here. So what is the final consideration of this work? We carry out a large-scale measurement campaign of 4G and 5G commercial cell network for a major mobile network operator in France over a period of 6 months, and we open source our datasets to allow further analysis of channel matrices and end-user performance aspects. Our findings reveals key performance KPIs, performance indicator KPIs of commercial 4G and 5G in terms of throughput, handover, behavior, impact of signal matrices on the quality experience of YouTube video streaming session. We study the implications of 5G channel matrix on quality experience of YouTube users with 1 second granularity play informations in terms of stall, resolution, video bytes downloaded, which is the smallest granularity both for quality experience of YouTube and channel matrices. We also provide analysis of the impact of handover on YouTube streaming during use cases such as mobility, pedestrian, static bus terminal, and static outdoor. And the demo of how to use this framework, it is available at this link. I will also explain in this video that how to use the framework and how to collect this YouTube and quality experience KPIs, and the datasets we generated from these use cases over a period of 6 months is available at this link. And thank you for this presentation. Now I will explain, or I will show you a demo of how to run this framework for the collection of 4G and 5G data sets using channel level matrices with 1 second granularity, and which is also flexible to choose, and it is also flexible to choose the player information that will show you next. Thank you.
Okay, in this video I will explain you about the second phase of my submission, which is the collection of YouTube QE logs with 1 second granularity and the channel level matrix, which is also with 1 second granularity. Okay, So first you need to run this application, which is GNetTrack Pro, which collects the channel level metrics with 1 second granularity, right? So I'm putting I'm starting a new session with new name. Let's suppose its name is 65, and now it started collecting logs in the background. Meanwhile, I made an application with the help of YouTube iframe API, which is which I put on my server with the name YouTube dir examples.com. Okay, and it will take the case and the video number. We actually choose 5 videos with all our 4K videos, and you can select your videos with your selection and your choice of your network scenario you're running. Okay, and here I'm putting 65. 65 is same as it is the same as we select previously. So why 65? Because we try to link between this YouTube QE logs and the logs of the channel level. Okay, so now it's running. So I choose video number 5, and now you can see it is running in, it is in HD 2160, right? Okay, and meanwhile I'm collecting the information which is on my server, and we have QE logs, and we name it 65. Okay, and if I sort by recent values, and you can see that we have this information. This is 65. Actually, we try to link this with QE logs, but I will show you later. Then so we have a video ID. Okay, and what is the current quality, and video bytes downloaded at that time, and load percentage is 13.6 percentage, and these are the available qualities we have in this video. And I am also saving the time and the date. This is also this is another way of linking the QoE log and the channel level metrics. But you also have 65 at the end. Okay, so now you also have player events, and the player events are, if I sort by recent, for this 65 we have 3 events. That initially there is a little stall, then the video is not started at that time, and then the video is running now smoothly. If I now press the pause button here, okay, and you will see here we have another event on the player, and it must here as 2. Okay, you can see that it's now 2, that video is paused at this time, right? And if I press it again, we again have another event. Now it will become 1 with the new instance, and the video will start playing again. Okay, so this is all about the QE collection from the YouTube with 1 second second granularity and the QE logs, and we have a QE logs. Meanwhile, we also have the player events. The QE logs, we have the QE matrices. We have the current quality, video bytes downloaded, loaded percentage, what is the variable quality, and if there came a stall, we have an event, at what time the stall came, and so on. So now I'm going to finish this this session. Let's suppose I terminate this phase session. Okay, and you also need to stop this log. Once you finish this log, it will automatically upload it on my server, and you can see it is on the directory, these log files, and I name it 65. Okay, and if I view this, you have lot of matrices which are timestamp, longitude, and latitude, where I collected this information, then the operator name, then the cell node, cell ID, okay, which I'm connected, then the technology I'm running in 4G, then the LT, and then we have level. These are signal level information, quality, signal to noise ratio. This is CQI, what is the current feedback given to the channel, and the LT, RSSI, and download bitrate and upload bitrate, with many other features. It more than 100 plus features with the information of also of neighbor cells and also. So what is the objective of this work is to find a relation between quality of experience metrics that we're collecting from the YouTube and the channel level matrices. So this is my second phase. So we started collecting with first with 4G, and now we are in the phase of collecting 5G information and data, and with different mobility cases, like for example pedestrian mobility in bus, driving case, crowded indoor outdoor, and so on. So this is all about my second phase. Thank you.